Hello, everyone. Thank you for coming to the presentation. Today we're discussing validating vulnerability analysis with a statistical analysis of metadata. I'm Alexander Bushkin. I've got co-presenting with me today Keith Grant, and fellow researchers Chess Hazlett and Marian also helped on this research. So for the first part, I'm going to turn it over to Keith. And Keith, you can take it away anytime you want, and just let me know when to switch slides.
Yeah, thank you, and thank you everyone who's here. All right, so first I'm gonna talk about what exactly we're talking about here. I recognize the title is a little bit vague, so I will start with the problem that we're trying to solve. I don't think it'll be news to anyone here that the number of vulnerabilities that are being reported every year is growing, and not only that, the rate at which they're being reported is growing as well. Despite that, we have roughly the same number of analysts per flaws, and so the math there means that we have more flaws for each analyst to handle, and that puts us in a spot where we have to decide, do we manage that by improving an analyst's cadence in analyzing a flaw, and if so, how do we do that? That's one thing that we're trying to understand here. So as a vulnerability analyst, I kind of think you can classify flaws into one of two ways. Well, there are many classifications, but one classification I think of often are you will encounter flaws that you understand almost immediately because you've seen many flaws like them, or you're very familiar with the technology, whether it's like the programming language or the component or project that you're working in. And then there are flaws that are not like that. There are flaws that, for whatever reason, are not things that you've seen before. And to be able to analyze those rapidly, one of the best things is to be able to find similar flaws. No two flaws are alike, obviously. That's why we have CVE. But there are a lot of similarities between flaws, and the industry has already created metadata to capture those similarities, to give us something that we can use to talk about flaws in a like-to-like comparison. So for example, CVSS and CWE are two examples of that, which we'll talk about later. And the other thing is we have a lot of data in Red Hat. You know, we have databases of architectural or databases of information about our vulnerabilities going back to, I think, at least the late 90s. Not all of that is relevant anymore, but that's one of the assets that we had to look at during this analysis. Is we have a lot of data about our past vulnerabilities. Next slide, please. So we're going to start looking at which metadata specifically we chose and how we chose to use it. Next slide, please. So there are three major types of information that we're going to use in this analysis. That is CVSS, CWE, and component. I'm assuming everyone here is more or less familiar with those, but I'll talk a little bit more about those in the future. And you can kind of think of those three as our independent variables and impact as our fourth, our dependent variable. Within Red Hat, we have four categories of impact for vulnerabilities. We have low, moderate, important, and critical. And being able to correctly assign an impact to a flaw at an early in analysis is important because the impact is basically what differentiates our level of effort. We obviously put the most effort into critical flaws, and for some low flaws, we'll only fix them if there's a customer request or something like that. So being able to get impact correct is very important for us, both to save ourselves unnecessary work if we classify something as too impactful, or to avoid having to rush later to fix something if we recognize later that, no, actually this flaw that we thought was moderate is important. So that's our challenge. And we're going to take a look at how we're going to use our metadata to answer that question. Next slide, please. Okay, so one of the ways in which we're trying to understand these flaws and trying to understand their similarity is through a method called cluster analysis. And if you haven't worked with this before, maybe you have done something like linear regression. And if you haven't done that before, the basic approach here is we're trying to look for ways that we can group flaws together based on their metadata, based on their CWE, CVSS, the component. And when we group them together, we're looking for natural clusters of flaws. And there are a couple of ways that we can look at this. So we can look at this either saying, to either answer the question of how many impact categories should we have? Like what's the number of impact categories that ideally match the data set that we have? We have 4 right now, and maybe it would make more sense for us to have, I don't know, like 6 impact categories, because it would make the boundaries between each of those categories clearer, and we would spend less time worrying about whether we're assigning a correct impact. Contrarily, we could do something like choose our cluster counts and say we want to have we want to find out how many impact categories we would need to have all of our flaws evenly distributed among them. Obviously, that's not going to work too well because flaws are different in impact by nature. So those are the questions that we're trying to answer. And to be able to do this form of cluster analysis, we need to be able to lay out our data in a reasonable way. Yeah, and I'm going to pick things up a little bit here. So let's go ahead 2 more slides, if you don't mind, and we'll start talking about, okay, yeah. So first we'll start with CVSS. The graph here is showing you some basic trivia about CVSS. You might not have done the math before yourself, but there are about 2,600 unique CVSS vectors. And out of those 2,500 unique CVSS vectors within our data set, we only have assigned 836 unique different vectors. But what this graph shows is it shows that even though there are that many unique vectors, there are obviously only 101 possible scores for each of those vectors to resolve to. And crucially, you can see that they're not evenly distributed. So there is already some bias built into CVSS in the calculations. And I guess I should also mention here that we don't use CVSS score as the primary determinant of impact. And that's the reason that I mentioned this here, is because we can't just use CVSS score to determine our impact. Okay, next slide, please. And here is a simple illustration of how CVSS vectors are distributed in our data set. And which vectors they are is not totally important. I put this here only to illustrate that the distribution of CVSS vectors in our data set is more or less a power law kind of distribution. We have a very few vectors that represent a lot of flaws, and then we have a long tail of vectors where there are not many flaws that are like that. And that is something to consider when we're looking for similarity, because we will find some flaws that are very easy to find similar flaws to, and some that are kind of unique. Yeah, next slide, thank you. So one of the things about CVSS is that it itself is a vector, obviously. It has a number of different elements to it, and each of those elements have a different number of values. What this text on the left here is showing you is we did some correlation analysis between each of the individual elements of a CVSS vector and how related it was to the final impact that we assigned the flaw. And our goal here was to find which of the CVSS elements in a vector are most informative of the final impact of the flaw in our data set. So this is obviously biased to our products. There are some observations here about which ones are most important that you can look at later if you'd like, but I will skip for right now. And let's continue. Yeah, okay. So my joke on the left here, you can see, you may have heard the phrase CIA triad to refer to confidentiality, integrity, and availability, the base parts of the impact score for CVSS. And I put them in a trash can only because, not because I think CIA is bad, CIA is great, but I think thinking of them just as a triad of 3 different elements is a little too simple. So one of our first approaches here was this notion of treating only CIA, only confidentiality, impact, and availability as its own space. Treat each of those different elements as an axis in a 3-dimensional space, which is helpful since they have the same number of possible values, and you end up with this kind of cube. So the green dot there in the center, you could think of as an origin of this three-dimensional space. And you can see the three axes labeled there. And the interesting thing about this is if you pick any value for CIA, none, low, or high, you can plot that within this cube of 27 different unique values. And by measuring the length of the vector from the origin to that, you can kind of get a sense of how impactful that flaw is based on CAA. But of course, this is already kind of duplicative of the score, because what we're looking for here is not necessarily just impact, but we're looking for ways to gauge flaws that are both similar and of similar impact. So let's go to the next slide. Right, so our observation here, when we were thinking about how we can express CVSS as a continuous value, which is to say, we don't want to treat each of the individual elements as their own dimension, because for some of those elements, like for scope, for example, there are only two possible values. So if we treat that as its own dimension, it's going to be extremely unuseful in clustering, because everything will fall into one of two categories. And then we're going to have basically our dimensionality will increase to a point where most of our matrices are very, very sparse, and that makes clustering very hard. So this is our way of ordering CVSS. And you can see on the x-axis here is our index that we've assigned to each of these CVSS vectors, and the y-axis here is the total score. Our motivation for doing this is basically a technique called mixed radix counting, where we count through each of the elements in a CVSS vector as though they were bases in a number system. There's a link there on the slide to the Wikipedia page about mixed radix math if you want to know more about it. But basically, you can see the ordering on the slide here that we chose, which is in order of what was most relevant to impact for us. And then you can think of it like let's say scope is the ones place, user interaction is the tens place, attack complexity is the hundreds place, so on and so forth. That's how we ordered these. The one key observation I'll make about this graph is that it obviously is not strictly in order of total CVSS score, but it does keep very similar flaws close to each other. And as you increase an index, we can guarantee a floor of a CVSS score. So we can't tell you necessarily how high high a CVSS score could be for a given index, but we can tell you that it will be at least above a minimum number, which is helpful, because then if we're dealing with one of those flaws like I was mentioning, where we're trying to determine the difference between a moderate and an important, we have a tool like this that we can use to find that floor of impact. Okay, so next let's move on to CWE. CWE is maybe a little bit more difficult, because we know that CWEs have some impact, some relationship to impact, excuse me, because obviously there are some CWEs that typically have higher impact, some that typically have lower. But here again, if we're trying to create a total ordering of CWEs, that's even less sensical than CVSS, because CWEs they don't represent anything continuous. Next slide, please. But one of our key observations here was that you can represent CWEs in a space in their own way, because CWE by design is already in graph form. You start with things like 699, which is a view, which contains categories, which themselves contain bases and variants, etc. So there's already a hierarchical structure built into CWE. And can we go to the next slide, please? And I will explain this in a moment. So the hierarchical structure in CWE, what that allows us to do is it allows us to create a continuous ordering of CWE that maintains similarity by creating this tree where we have all of the parents, where we order CWE in that hierarchical sense based on its It's actually a directed graph structure because there are a few loops because some CWEs have more than one parent. But then if we do a depth first search on that graph, then that will give us an ordering of CWEs that again maintains similarity. And the reason that I put this graph together, the coloring here is gray are CWEs that were not included in our data set. And for the most part, those are CWEs that we shouldn't be assigning because they're, let's see, not variance necessarily, but categories, things like that. CWEs that are labeled in white here are kind of middle impact. And then yellow into green is less impactful, and orange into red is more impactful. The thing that I'm hoping to illustrate with this slide is that our intuition was borne out. It's not entirely perfect, but you can see here that clusters of CWEs that fall in the same place in the hierarchy have similar impacts. These impacts that we've determined are based on the most common impact in our data set for that given CWE. Next slide, please. And then, so the third element that we were looking at, the third metadata part, was our component. And this is what software is affected, like we're talking about kernel or something. And we could, and we tried just arbitrarily ordering these something like alphabetical order. But one of our key observations was that there are, because of how we represent components in our data set, sometimes we'll have something that's sort of generic, like kernel here, but then we also have components for subsystems of the kernel, like memory management, KVM, things like that. And so in ordering our components, we did choose to order them kind of arbitrarily, but if you think of each component, like each basic component, like kernel here, as being placed on an integer on a number line, we then divide that integer between all of the different subcomponents of that component. So excuse me one moment, I'm going to take a closer look here. So you can see like kernel would be, kernel falls into the first bucket. Kernel KVM will be between 1 and 2, and kernel KVM NVMX will be even, we'll further divide that space so that we end up with a number line that has all of our components in an order that keeps similar components and subcomponents next to each other. And with that, I will hand it over to Alex, who's going to show you some of our results.
Thanks, Keith. So now that we kind of explained a bit the approach into how we wanted to encode the data and kind of, let's say, pre-process it, let's look at essentially what the clustering results showed. So before that, let's get to the actual data set, right? So right now we've been talking about CVSS, we've been talking about CWE, we've been talking about the components and how we wanted to use them. Another important consideration was obviously the data set. We decided to restrict ourselves to the past 4 years of data just because it was easier to manage, let's say, with respect to, fairly similar ways of handling it, right? Like one of the key points, one of the key takeaways that we're trying to say is that you have to consider not just bias inherent in the data, obviously, but you have to consider the bias in the context that creates the data. So that's why we had considerations like, for example, not all CWE IDs that we had assigned to vulnerabilities were within the 699 and the 1194 views. We tried to restrict ourselves to like the software development, the hardware development view. And of course, then there's considerations about like what to do with chaining or with ORing. Similarly, in terms of the skewing, we had an overrepresentation of kernel flaws, right? Because as we know, kernel.org has published numerous amounts of flaws over the past year and a half, and that leads to overrepresentation. In particular, if we consider the fact that by default, the way that we handle vulnerabilities is they come in with a 5.5 until they get analyzed. And once they get analyzed, then the score changes. But if we have like a lot of lows and moderates or just flaws that we're not able to get to analyze in time, that can lead to a skewing of the data. So essentially what we started with was those 14,000 flaws roughly from those 4 years of data, and we reduced it down to 7,415 flaws, which was what we actually used to perform the clustering and what we, attempted to kind of make sure was consistent in terms of the kind of data. So making sure that they were all within this, for example, all within the 699 view or the 1194 view. So in terms of clustering, when we look at components, it worked kind of the way we wanted it to, right? The objective was not necessarily to have an inherent order, as in from left to right demonstrates something in terms of impact as being more important, but rather the prevalence of a specific product or of a specific component in the vulnerability data set. Since kernel publishes a lot more flaws, we have a lot more representation of kernel, and that's what we ended up with when it got assigned essentially into the bucket at index 1. So that's why you see this like big swarm of data or of data points on the left-hand side of the component axis. As you go right, you can see that it peters out. That's more so just the fact that, there might be a product that only ever showed up once in those 4 years worth of data. So it only gets, 1 point. If we look at CWE, the spacing is a little bit more difficult. It's not as obvious visually what it can tell you. Partly that's because, the 699 and the 1194 views, we did use depth-first search in terms of how we mapped the nodes, but there's overlap between just IDs, right? So there are going to be IDs, for example, in the 1194 view that might be in the 300 range, just like there are some from the 699 view. The big thing with the gaps here that you can say is that there are specific parts where no Red Hat products are impacted by those specific weaknesses. But the CWE axis in itself, when we're going to describe it a little bit later on, it's less visual, but it does help explain how some of the clustering happened, let's say. If we look at CVSS, right, we spent a lot of time explaining the modulo system. It worked the way we wanted it to work. Essentially, we were grouping flaws by similarity, not just inherently the score itself, which is why you can see this banding effect. Obviously, part of the banding effect is, like Keith mentioned at the beginning, there are certain score ranges that are just unreachable, and so that's going to be consistent throughout. The other thing that you can note is that there is, for example, so let me just quickly explain the coloring. Green is low, blue is moderate, yellow is important, red is critical. So you can see that there's a consistent banding of primarily moderates, right, which is mostly what we end up seeing, that goes all the way through. What we're going to see in a minute with the band analysis is that the actual CIA impact is what changes. The reason that we see moderates that even end up at that high range, right, at the top of what could be the most severe CVSS impacts, is because this is where the other, let's say, components of the CVSS vector come into play. If CIA is, the main impact factor, what can change something from being moderate or important or critical or low could be all the other factors, right? The attack vector, the privileges required, the complexity, things like that. So looking at the first band, obviously, I apologize for the names. We're not exactly creative, but we called it DOSville. Essentially, the idea here was that based off of a very simple analysis of what was the most prevalent CIA values for those vulnerabilities in that cluster and the corresponding, let's say, CW and CVSS ranges, we saw that primarily it was DOS-like behavior. So, only availability is impacted. If we look at band 2, configurationville. So similarly, we saw primarily an impact being on the confidentiality value of CIA. However, it's low, right? So that tells us that, okay, you're compromising something, but it's probably not very important information. Keep that in mind when we get to band 4. In band 3, this is kind of the mixed bag, right? It's in the middle of roughly, the least severe to the most severe CVSS scores. So it makes sense that here's kind of that range where it's difficult to define a specific trend. This is kind of where you find those, okay, low impact on confidentiality and integrity. That could be a lot of things, right? There's not a specific thing, but that makes sense, right? We're in the middle of the road. Band 4 was interesting because similar to band 2, now we have the same sort of thing. We called it Pieville because now the confidentiality impact is high. So this is where we're getting to the kinds of vulnerabilities that are, are impacting confidentiality, and it's sensitive information that is being compromised. Band 5, data manipulationville, again, very creative name. The idea here is we're starting to see, the more severe kinds of flaws. So CIA, CI are high in terms of impact. That's, in line with things getting more severe. And if we look at band 6, worst case, right? This is everything's high. everything is as bad as it could possibly be. The key takeaways, though, from those sorts of banding things actually come in when we look at the CWEs that were most common for each of the bands. So, for example, in that low range, what we call DOSville, the most common CWE that we found was 401. Now, 401 is defined as missing rebase of memory after effective lifetime, right? So that's the sorts of vulnerabilities or weaknesses that can lead to vulnerabilities that lead to memory exhaustion. So the typical things that could lead to a denial of service over time. Similarly, in that 2000 to 2500 range, what we call data manipulationville, the primary thing that we saw there was improper handling of extra values. That kind of weakness ties into things like buffer overflows, ties into like out of bounds reads, writes, the things that can get you to remote code execution, that can get you to RCE, things like, oh, well, yeah, remote code execution, writing over memory, essentially things that compromise CI in a significant manner. So far what we've done is we've kind of explained the approach in encoding the data, which was the primary thing, and we showed some initial clustering. There's obviously a lot more that can be done with taking this research further, which we have the intention to do. And I'm going to turn it over to Keith for the first 2 points.
Yeah, so some of the first things, now that we have this space where we can plot all of our vulnerabilities, both historically and as we analyze them, we can ask some questions like, given all of the metadata for this flaw, is anything about it unusual? How similar is this flaw to its neighbors in that three-dimensional space? And our hope is that we will be able to use that to identify either flaws that we maybe have not analyzed correctly in the moment, or flaws that were analyzed in the past that warrant some more closer investigation. While at the same time, we don't want every flaw to become too similar to all of its neighbors, because then we end up losing the unique qualities of each vulnerability, and we end up regressing to a mean where every flaw is just the same thing. That's what we want to avoid. Because sometimes flaws are actually outliers. Sometimes flaws are unlike flaws that we've seen before. But at least if we can look and we can validate that and say with certainty that we understand why it's different, that is of benefit to us.
Yep. And taking that further, one of the nice things that would be useful for analysts, right? Because all of this comes back to how are you analyzing vulnerabilities, especially with a high volume and a lack, let's say, you're constrained on resources, right? So what would be helpful is if, while an analyst, in our case at Red Hat, is working on analyzing a flaw and they're messing, let's say, with the metadata values like CVSS, CWE, and they have the existing component list, geolocating within that cluster space where, based off of those values, a flaw is starting to, what neighborhood it's showing up in, what band, that's where we start thinking about presenting the analyst with similar vulnerabilities, doing something like a distance function to find the 4 nearest neighbors. Not so much to automate the process of analysis, but to kind of assist, to say, look, you're in DOSville, right? You're in a low impact area. The CIA value is none, low, right? So keep that in mind while you're analyzing this flaw. It could be something that is within that neighborhood that has similar characteristics to flaws that you've already analyzed. That's one thing that we're working on. Obviously, the other one is improving our methodology. I think that's kind of par for the course, right? I mean, there's always better search techniques and data structures that we can use. We can think about how we handle chaining better. We can think about how, we could rethink, how we're querying our data set, things like that. Speaking to the point of outlier, we wanted to kind of end on this one because we had this particular critical in the second band here in the 500 to 1,000 range, which was the only critical there. And we kind of went to look at it, because like, maybe this is one of those cases where something was mislabeled. Looking at the vulnerability, which happens to be this CV 2024-4896, which, by the way, we weren't impacted, so that's good. It's kind of a unique case where it's one of those rare cases where you have a triad that's none, high, right? There's no confidentiality impact, but you do have a high integrity and availability impact. In this case, it happens to line up. It is correct, because it's one of those situations where you could be with libyaml parsing some sort of user config, right? Your vulnerable to this external entity, which could allow for, some sort of like remote code execution, or it could lead to some sort of DOS, right? Because you're pulling in unverified external entities, but at the same time, you're parsing a user config file, so there's no confidentiality there being compromised. So this was just an example of like verifying that, actually, yes, it is correct where it's found. So, anomalies sometimes are anomalies. But there's a lot more that we can think about doing, which we intend to do moving forward. So, Keith, any final words, or should we sign off?
No, I think we're at our time. So
Yeah.
thank you for, if you, I will say, if you have any questions, feel free to contact us offline, and we would be happy to talk about this, because we're going to continue with this research, as Alex said. But thank you for attending.